Okay. Yeah. Okay. So in this session is all about image formation and enhancement, right? We'll see how image is basically formed, right? And what are the different image enhancement techniques we have. I cannot discuss all the enhancement techniques, and we'll see what is the role of these image enhancement techniques while designing computer vision system, right? So I'll start with the image formation process. You might have also seen these things earlier somewhere, right? So there's a light source. There must be a light source which falls on the surface of, especially the surface of the object, and object surface you can say, and then it gets reflected, pass through the imaging plane, and it reaches the sensor plane via lens, or you can say via optics, right? So what are the different, you can say, factors that influences this image formation process? One is the light source, right? Very, very important, right? The light source, the illumination of the light source, right? You can say, and the light source strength, direction, surface geometry, the material, the kind of material, right? Especially I'm talking about the material of the surface and the nearby surfaces as well, right? From where it gets, some of the things gets reflected. The sensor capture properties are also very, very important, right? For image formation, and the image representations and the colors. So these are some of the factors which influences the image formation process. How can we define an image? So before that, let me show you the whole electromagnetic spectrum, which you might have seen in physics, right? So you can see that this is how the whole electromagnetic spectrum looks like. And there's a very narrow portion over here, which is nothing but the visible spectrum, which we can see. And on the one side, you can find out infrared, and the other side, you can find out ultraviolet. But this visible spectrum is only a narrow portion out of the whole electromagnetic spectrum. And we'll see the concept about colors and all later on. What is an image, right? So very, very important, because in computer vision, the input itself is an image or video. So we must have to understand what is an image and how can we represent an image. So those who have already studied signal processing, right? So they might have studied that yes, signals can be represented with the help of a function, right? So in digital signal processing, especially you have studied one-dimensional signals, and where the one-dimensional signals can be represented in the form of f of t, right? There's only one variable of area, that is t, right? So t versus f of t. So there is a one-dimensional signal can be represented in the form of a function, which is nothing but f of t, right? So this could be any signal. You might have seen any signal also. Let's say maybe you can consider any sinusoidal signal over here, but this is t and this is f of t, right? So any signal, one-dimensional signal, can be represented with the help of one dimension, or you can say a function or 1D function, which is f of t, or you can consider this as x or this as f of x also, right? But in case of image, it is nothing but a two-dimensional signal. Image can be considered as a two-dimensional signal, and image is nothing but a two-dimensional function, which is f of xy, right? So x and y are the two different variables we have here, where these x and y are nothing but the coordinates, the spatial coordinates. I'll talk about it later on. What do you mean by spatial coordinates here? And this f especially is known as the amplitude at that particular value. So here also I can say, let's say this is t. Let's say, for example, this is t1 and this is f of t1. This f of t1 is nothing but called as the amplitude, right? So in our case, it is just amplitude at this particular position, or you can say coordinate x and y. So what do you mean by this amplitude here? Then this amplitude in case of an image is also known as intensity, or you can say the color value or the gray levels of an image. So xy is nothing but the coordinates, right? And f of xy is nothing but the color value at that coordinate. So you can say the intensity or the gray levels of that particular coordinate, x and y. How can we define this f of xy? Because we know that image is dependent on two things. One is the light source, right, which is the illumination function over here, the amount of light basically that falls on this object surface. And second is very important, that is the reflectance property of the object, right, of the surface, you can say. So this function f of xy can also be written as I of xy into r of xy. What is I of xy here? F of xy is nothing but the image. I of xy is nothing but the illumination function, the amount of source illumination incident on the scene being viewed. This is the amount of light that falls on the object. That is I of xy if it ranges from 0 to infinity, right? We are now talking about the continuous image, right? Whenever we are taking the image, that is continuous in nature. So it is the camera which helps us in converting the analog scene into a digital scene, right? So there's the A to D converter that is present in the image, which helps in converting that analog image into its corresponding digital one. We'll talk about what are the stages involved there to convert the analog image into its corresponding digital image. So let us now look at the two terms, right, which is nothing but I of xy and r of xy, and if you just multiply them together, you will get f of xy. What is r of xy? That's the reflection function, which varies from 0 to 1. So I said 0, that means all the light, right, is being absorbed by the surface of the object. So that means it is a total absorption, you can say. And 1 is like total reflectance, right? So I mean r of xy, that's why lies from 0 to 1, where 0 is total absorption and 1 is total reflectance. And I of xy lies from 0 to infinity. So the value will in total lies from 0 to infinity, which you don't want, because we ultimately want to process the images with the help of a digital computer. So we don't want to, you can say the value, right, that should be equal to the infinity and all. So we need actually some process to convert this analog, or you can say this continuous values into its corresponding digital values. So what are the two stages that are involved in converting, right, this analog image into corresponding digital image is nothing but sampling and quantization. You might have heard about these two processes, where sampling is required to digitize the coordinate values, that is f of that is xy. We want to also, right, digitize the coordinate values. At the same time, we want to digitize the intensity values or the amplitude values, which lies from 0 to infinity. So right, sampling helps in digitizing the coordinate values. Quantization helps in digitizing the amplitude values, and ultimately what you will get is a digital image, right? So when the spatial coordinates, which is xy, and the amplitude values, the intensity values, are all finite, right, or discrete quantities, the image is known as digital image. And the process that helps in converting the analog image into digital image is nothing but sampling and quantization. So image can also be represented in the form of a matrix. So you can see, right, the matrix is a two-dimensional matrix over here, right? And where the matrix elements are nothing but f of 0, 0, f of 0, 1, so on up to f of 0, m minus 1. And here it is f of n minus 1 to f of n minus 1 to f of n minus 1. When I say f of 0, 0 over here, this f of xy is now can be represented with the help of a matrix, which, or you can call it as a two-dimensional array, which contains values, especially the intensity values, right? And where this f of 0, 0 is nothing but the intensity values at the position 0, 0. So what is the coordinate system of the digital image? Where is the origin? So this is where actually the origin of the image lies. This position is actually 0, 0. The next position is 0, 1 over here. So here the x-axis is vertically downwards and the y-axis is actually horizontally rightwards, right? So this is how actually you need to represent an image, right? The coordinate something, the origin is something is in the top left hand corner, which is 0, 0, right? So the intensity at this particular value, and the intensity at this particular coordinate is known as f of 0, 0. The second one is f of 0, 1. That means the color values or the intensity values of these pixels. So image basically consists of number of pixels, and every pixel is having two things. One is its coordinate and one is its corresponding intensity values. So when I say f of 0, 0, it is the intensity value. When I say it is 0, 0, it is nothing but the coordinates. So this image is particularly having size m cross n, because there are n number of n cross m, where there are n number of rows and m number of columns. You can say it starts from 0 to n minus 1. It is 0 to m minus 1, right? So there are n number of rows and there are m number of columns, right? So that means how many pixels you are having. The image size is known as n cross m. This is how we can write the size of the image, which basically tells us the number of rows, or you can the number of rows and the number of columns that are present in this image. And if somebody will ask you how many pixels you are having, so we are having n into m number of pixels in this particular image, right? And this is the convention which we follow for an image, where the origin is at the top left hand corner and the x-axis is vertically downwards and the y-axis is horizontally rightwards, right? And this is how we can represent, and this is how you can store the image in a digital computer in the form of a two-dimensional array consists of number of pixels, right? Where the pixels are having two things: one is its coordinate and one is its corresponding intensity values. I mean the color values, and this color values is dependent on two things. One is the light source, and the one is the reflectance properties of the surface, right? So this is all about the definition of the digital image, right, in the form of a function in the form of a matrix. And also we discussed the process that are involved in converting this analog image into its corresponding, right, you can say digital image, right? Sampling quantization we have already discussed. Now we will talk about the types of the digital image we have, right? So before I discuss the type of the digital image, we must discuss what are the different when I say k-bit image or 1-bit image or 8-bit image, so how many colors will be having or how many tones will be having, and whether more number of colors are better for us or whether less number of colors are better for us, right? So the k-bit image in general, right? If the image is k-bit, it all depends on the number of quantization levels you have used to digitize the image. So in general, we use 8-bit image, which is a grayscale image. So if the image is 8-bit, that means you can represent every pixel value in the form of 8-bit binary number, right? So the color values in this case will lies from 0 to 2 to the power k minus 1, right? To the power k minus 1. That means 0 to, in this case, 255, where 0 stands for black and 255 stands for white. So if you are dealing with 8-bit image, so your color values will be lying from 0 to 255, right? So it is from, like as I mentioned, 0 to 2 to the power k minus 1, where k is nothing but the number of bits you are using to denote every pixel values, and where 0 is nothing but black and 255 is white. Fine. If you are using, let's say, 1-bit image, so it will be like 0 to 1. So in that case, you will be having only two colors, that is 0 and 1. We call it as a binary image. We'll see what is the difference between a binary image and this 8-bit grayscale image. Which one is better for us? Whether more number of colors is better or less number of colors are better, right? You all know that more number of colors are better. I'll also show you one example, right? This is, I mean, there are two terms which are very important here to understand. One is the dynamic range and one is in image contrast, and how this image contrast is related to this dynamic range. We'll also see later on. And whether this dynamic, what do you mean by this dynamic range? First of all, this dynamic range of an image, in this case, in case of 8-bit, is here 0 to L minus 1. L is nothing but here 256. That is 2 to the power k. That is 256, right? So L minus 1 is from 0 to 255, right? That is known as the dynamic range, right? From 0 to 255, right? That's the range we are using here for the whole 8-bit image over here, which can be easily normalized to 0 to 1. In some of the applications, you may require to convert from this 0 to 255 the pixel values, or you can say the intensity values, from 0 to 255 to 0 to 1. So there are very simple procedures to be followed to convert from here to here, right? You can just divide 255 by all the values, pixel values, so you'll get the values from 0 to 1. That's the simplest way to convert from 0 to 255 to 0 to 1. Contrast. Contrast is a very interesting, I mean, very important term here to understand. So contrast is associated with the dynamic range. How can we define this image contrast? It is nothing but the difference in intensity between the highest and the lowest intensity levels, right? So that means contrast is nothing but the difference in intensity between the highest and lowest intensity levels in an image. So the more is the contrast, you can say the more is the dynamic range, right? Or you can say the high dynamic range image is having good contrast because the dynamic range is good. So you can say even the contrast of the image is also good, right? So that means the poor dynamic range images are not good contrast images. So they are poor contrast images. If there are very, let's say, out of 0 to 255, you are only using 10 to 20, the pixel values 10 to 20 to represent one image. So this would be definitely a poor contrast image, right? I'll show you later on, right? Because the dynamic range here is very less. It is from 10 to 20. It is not from 0 to 255, right? So the dynamic range should be large, or you can say high, to have a good contrast image. We'll see how to, even if a poor contrast image is given to us, how to use some algorithms and to just enlarge the dynamic range of an image. And if you know that how many bits are required per pixel, you can easily compute the size of the image, because you know that how many pixels you are having. Image consists of number of pixels. You know how many pixels you are having by looking at the size of the image. If one particular pixel is taking let's say k bits, so you can just compute how many pixels you are having, multiply by a k number of bits, right? You will get the number of bits required, right, to store that image. You can just find, then you can represent in the form of kb, mb, whatever you want. So now let me show you the types of the digital images we have. I'll start with the binary image first of all. So when I say binary image, it is a two-tone image. That means it's a one-bit image where the number of colors will be 0 and 1. Let me show you that picture and ask you something. So this is an image, right? This is an image you can see over here, binary image, where there are only two colors. Every pixels in this image is either holding a value 0 or 1. So 0 stands for black, 1 stands for white here, right? And this is, they look at this person actually. These are the actually values. You can say the pixel values or the intensity values of particularly this region, a small region, because I cannot visualize all these pixels. It's a very large picture, right? I cannot visualize all the pixel values in this slide. So I've just taken a small portion over here, and now you can see over here, all pixel values are holding values either 1 or 0. And you can see if you look at closely this particular region, there are white pixels, right, and then followed by black pixels, right? You can see over here. So white pixels are nothing but like these are all white pixels, and these are all black pixels. You can see over here, and similar type of image you can see over here. So now, if I ask you here, if I ask you one question, that what is the brand of the bike, right? What is the brand name of the bike? Probably you will face a lot of difficulties to tell me what is the brand of this bike. It is there in this image, but not exactly visible to us, because there are only two colors through which you are trying to visualize everything in the image, right? So there are a lot of informations which are missed, which cannot be visualized using only two tones. Let me show the corresponding grayscale image of this particular image and try to find out the same, try to answer the same question: what is the brand name of this bike? This is a grayscale image which we have just now talked about, which is 8-bit image where the color values lies from 0 to 255. And again, these are nothing but the pixel values, right? For this corresponding to this particular region over here. You can see over here. Fine. And the values you can see lies from lying from 0 to 255. And now if I ask you the same question, right? Of what is the brand name of this bike? Probably you can tell me yes, Suzuki, right? So it is visible. That means now when we have increased the number of colors from 2 to 256, right, which is from 0 to 255, now many things are visible. So it is visually better, right? The appearance of this image is better, right, compared to the binary image. So from here we can conclude that yes, the number of colors, right, what I mean when is required, right, in case of 8-bit is really crucial compared to the 1-bit image. If I show you a color image over here, which is RGB, right? There are different color models. We have RGB, CMYK, and other color models which are used in other industries like printing industries and all. But what is important for us to understand, what do you mean by RGB image? So in case of RGB image, you might have seen that every image or every pixel in this image will be having three intensity values, one in the red plane. If you consider the first pixel over here in this particular region, if you first consider the first pixel over here, so every pixel, as I mentioned, in this particular image will be having three different values, one in the red channel, one in the green channel, and one in the blue channel. And the combinations of this 132, 201, and 120, right, corresponds to a color in a color image. So every color image will be having three different planes or channels: red channel, green channel, and blue channel. And in every channel, right, again, every channel, you'll be having values lying from 0 to 255. So that means this is a 8-bit one, 8-bit image, green is an 8-bit image, red is also an 8-bit image. In total, it is a 24-bit image. And the number of colors possible in this case, it is 20 to the power 24. So these are the possible number of colors. The values will be from 0 to 2 to the power 24 minus 1, but the number of colors possible is 2 to the power 2, which is a large number. So those many numbers are you can form those many colors, and this number of colors, I think, are sufficient to represent any object across the globe or across the color. So now if I ask the same question, right, I mean, if you just compare this image with this image, right, so there are even many things which are visible here which was not visible properly in case of grayscale image. So that means, right, the colors are helping us in identifying several, or you can say recognizing several crucial patterns that are present in this image, which was not even possible in case of binary image. I mean, some of the informations are still missing in grayscale images. So color images are very, very important in this case, right? So to get more details, you can say. Fine. Now, before I discuss, the concept of neighborhood and all, so let me show you two interesting concepts. One is spatial resolution and one is gray level resolution. What will happen if I reduce the size of the image, and what will happen if I reduce the number of colors, right, which we already discussed, right? If I reduce the number of colors, what kind of effect we find? And if I reduce the number of, I mean, you can say the resolution of the image, basically the size of the image, what will happen? So based on that, there are two concepts. One is spatial resolution and one is gray level resolution. So spatial resolution is nothing but the smallest discernible detail in an image, right? So you can see over here, there's an input image given to us having size 1024 into 1024. And now this image is particularly downsampled to 512. 256 means these are all square images, 256 to 256, until 32 cross 32. Now what I will do, I will resize these images, especially 32, 64, 128, 256, and 512 to 1024. That means I will try to resize the image, right, from 32 to 1024, and then I'll show you some of the effect, right? You can see the effect. This is like the original image, right, which I've shown to you, and this is the image which has been resized from 512 to 1024. This is 256 to 1024, 128 to 1024. You can see some degradations over here, especially in the boundary regions, you can see. And these here you will again find some of the blocking effects. We call it as a checkerboard effect. Especially you will find in 32 cross 32. So what we have done here is the 32 cross 32 image is given to us. We have resized, right, into 1024 and 1024. So what is going to happen here is you will find the checkerboard effect over here, right? So you're not able to find out the patterns. The most of the informations are lost. So if you reduce, right, if you are resizing the image, you need to be very, very careful while resizing the images, right? Because sometimes it is required while solving the real-time problems because of the model compatibility and all. You need to resize the image. So there are different interpolation techniques we have to resize the image. You might have heard about something called as nearest neighbor interpolation. Nearest neighbor interpolation, one of the most popular one, but not a good one. Then bilinear interpolation, and then there is something called as a bicubic interpolation. So these two are very, very important, right? There is a function available, right, in OpenCV, and I mean resize function available where it always asks to choose the type of algorithm, right? Especially whether it is nearest neighbor, whether it is bilinear, whether it is bicubic, right? That you need to also check, right? On the same image, 32 plus 32, you can also apply bilinear, you can apply nearest neighbor, you can apply bicubic and check which of the algorithm is giving best result. But the kind of effect you will find in this case is nothing but known as checkerboard effect. The second one, I mean, especially when you are reducing the spatial resolution and then resampling it to the original. At that time, you will find this kind of problems, right? So the next one is effect of varying the number of intensity level. That is the gray level resolution. What will happen if you will reduce the number of colors, or you can say the number of intensity values, right? Or you can say the number of gray levels, right? The different names we are using. Fine. So this is the original image where we are having the intensity values lies from 0 to 255. That means we are having 256 number of colors. Now you look at the last image. What is this? Who can tell me? What is this? The last one. The last one is nothing but the image where there are only two colors. That means we are exactly. Thank you. So that means the last one is nothing but the image where there are only two colors. That is 0 and 255. That is black and white. And what you can observe here that all informations, whatever the important information we have here, all the structure of the bone, the patterns, whatever is available, the skull, and everything is not at all visible over here. And even in this case, whenever you are increasing the number of tones from 2 to 4, still no informations are visible. And when you are considering 8 number of tones or 16 number of tones, these are the some important, these are some crucial or additional things you may find, right? You can see over here, it is given some, contours to us, which was earlier not present, which was not at all present in the original image. So these are known as, you can see a lot of contours you will find over here. And this is actually known as false contouring effect. So you may encounter false contouring effect while reducing the number of number of gray levels intensity values, right? So we need to be very, very careful while reducing the number of color or intensity values, or you can say the gray levels. So that may sometimes lead to false contouring effect. That means this is not there in the original image. Fine. So these type of things should be avoided. So we should not take then less number of colors at least. But if you take 64 colors or 128 colors, probably you will not find any difference between these two, right? Because even 128 number of tones or colors are here, you can say sufficient to at least capture all the informations. And why you are discussing, why you want to actually reduce this? What will happen if you reduce this? Of course, if you reduce the number of colors, you can also reduce the storage capacity of the image. So that means if I'm choosing a binary image, of course, the size of the image is going to be very, very less compared to this, because every pixel in this case is taking, or you can say 8-bit, right? And if similarly, you can compute the number of bits required for each of the pixels that are present of the image. And if you can represent it within, with let's say 6 number of bits, or you can say 6 number of bits or 5 number of bits, obviously the number of or you can say the size of the image is going to be less compared to the original image. This is a major goal, but it should not also lead to any false contouring effect. So this type of effect, checkerboard effect, false contouring effect, you may encounter while reducing the number of color values, while reducing the number of, and while reducing the size of the image. So you need to be very, very careful while resizing and while reducing the number of gray levels or intensity values for solving a problem. Before I discuss the image enhancement techniques, let me also talk about the neighborhood of a pixel. Very, very important concept, right? And even in convolutional neural network also, we will find out the concept of neighborhood, right? So we all know to whom we call as a neighbor, right? So the people who are living, around us, we call them neighbors. So similarly for a pixels, the neighboring pixels are nothing but the pixels which are close to the the pixels which we are considering. So there are 3 different types of neighbors we have. 1 is 4 neighbor when we are considering only. So let's say 4 neighbor. 4 neighbor, 4 neighbor, 4 neighbor. So let's say 4 neighbor when we are considering only 4 neighbor. 4 neighbor when we are considering only 4 neighbor. So let's say 4 neighbor when we are considering only 4 neighbor. So let's say you are, let's say there is an image given to you, and let's say there is an image given to you, and there are a lot of rows and columns. That means the image is having size, let's say m cross n, and you are somewhere here, right? You are somewhere here, and if somebody will ask you what are the different neighbors you can have, so we can have three different types of neighborhood models. One is n4p. P is the actually the pixels which you are considering, and n4 is nothing but the four neighbors of this p. When I say four neighbors, these are nothing but the two horizontal neighbors, these two, and these two, vertical neighbors. And if you look at the coordinates over here, the p, which is the pixels which you are considering, if the coordinate of p is xy, so the x is, x will increase downwards. So that means the next value of the x towards this, because we know this is x and this is y, right? This is how we can represent an image. We discussed the convention, right, which we follow. And if we are x is this, if this is xy, so this will be definitely x plus 1, and you are still in this yth column, right? And this one will be, you are in the xth row, and this one will be y minus 1, this one will be y plus 1. So similarly, you can compute all other coordinates. Very, very important for us to know even the coordinates of all the neighbors. So whenever you are considering the two vertical neighbors, two horizontal neighbors, we call them four neighbors. There are also another diagonal, another neighborhood model you can say, which is known as NDP, the diagonal neighbors. So whenever you are choosing these four, the neighbors of a particular pixel P, they are known as diagonal neighbors. So you know how to compute this, you know how to find out the coordinates of this. This is x minus 1, y minus 1, right? So this is how x is increasing, this is how y is increasing, so this is y, so this will be definitely y minus 1. So this is x, so this will be x minus 1, this will be x plus 1, like this, right? So this will be y, so this will be y plus 1. So accordingly, you will get all the coordinates over here, right? So, but what is important for us is this one, right? Mostly this is going to be useful, this 8 neighbors, right? So when we say the 8 neighbors, it is nothing but the union of this 4 neighbor. That means I can just write n8 of p is nothing but the 8 neighbors of a pixel p, which is nothing but n4 of p union nd of p. So if you are considering all these, horizontal neighbors, vertical neighbors, and diagonal neighbors, that will become n8 of p. That is the vertical neighbors, right? Vertical neighbors, horizontal neighbors, and the diagonal neighbors. That is n8 of p. One thing you can also see over here, that the pixels which are present in the boundaries, like these pixels, right? The pixels which are present in the boundaries, like these pixels, will not be having 8 number of neighbors. Are you all agreeing with me that these pixels will not be having same number of neighbors compared to these pixels, these middle pixels? Yes, these pixels will not be having 8 number of neighbors if you are considering N8P, right? Because these are such the neighbors which are not present over here. So we'll see, I mean, how to deal with these problems, right? If you are applying something over each of the pixels where you need to consider all the neighbors, if it is not there, then how to deal with this, right? So we'll talk about something called as a padding concept, right? In convolutional neural network, where also we can use the concept of padding and different types of paddings we have, right? So, this is all about actually the neighborhood of a pixels and how to compute the neighborhood of a pixel. And 8P is very, very important for us. There is another actually term which is very important. I will not go into the details of this connectivity and all. What is the meaning of connectivity? How would you know that two pixels are connected, right, in an image? So the two pixels will be connected if they are adjacent in some sense, right? Let's say this is an image which is given to us, right? And where the P is and one and pixel and Q is another pixel. So how would you know whether P and Q are connected or not? So either this P and Q are the neighbors. They can be of any neighbors, N4P or NDP or N4P. Either they are the 4 neighbors or diagonal neighbors or 8 neighbors. And the intensity values, right, are same. There are two conditions here. They must be the neighbors, right? And the intensity value should be same. So I can just choose one as a value here, because for simplicity, I'm taking a binary image where this value is 1, this value is 1. So I can say these two are connected. How they are connected? Because if this is a 4 neighborhood of this pixel, and this is also a 4 neighborhood of this pixel, and their intensity values, right, are similar. And these two are also connected. If it is 1, they are neighbors, diagonal neighbors, and the intensity values are same. These two are like this. And if it is if this is 1, this is 0, they are not connected because the intensity values are different, right? So this connectivity is a very important concept, right? And a very important concept to know about the object boundaries, right? So let's say, for example, there is an image having two different objects, right? So by connectivity, you can group the pixels and tell that these pixels belong to one object and these pixels belong to another object. But what is most important here is to tell, right, the connectivity between the two objects. So that means if the pixel, right, basically we're talking about, so this is a segmentation problem actually, where your task is to just segment different objects that are present in the image, right? So if you can say that yes, the connectivity, if you can find out connectivity in this case and tell the pixel values with one are connected. Let's say those who are connected, the pixel values, all these pixel values are one, let's say over here. And if they are connected, they belongs to one region. And if they're not connected, to other set of, right, other set of, you can say objects, or you can say other set of pixels which are connected, right? You can say that these two are different. So this is how actually you can just apply the connectivity concept, right? You can just go through it if you want to know more about it. There's a connected level, labeling algorithm available, right, through which you can just identify whether the pixels belongs to one particular object, and how do you know actually that these belongs to one object and this belongs to another object. So finding connectivity is not a difficult task, but identifying, right, whether they belong to a particular object, they belong to another object, is very important here, right? To know about the property of the object and all, so many things. So okay, there are also other concepts like adjacency. Yes, two pixels, those who are present in the different neighbors are so to be adjacent to each other if they are connected in some sense. So similarly, you can just go through some of the concepts of connectivity and adjacency. They are very similar to each other. Fine. So next concept is image enhancement. So before I discuss image enhancement, let me talk about the traditional computer vision system, and why do we need actually image enhancement in this particular FTP. Traditional computer vision system, and what are the stages involved in traditional computer vision system. Stop. Let's say your task is a simple task. Your task is an image classification task. I have already shown you what do you mean by image classification. I've shown you a couple of image classification tasks today, where your task is to just classify an image or assign a label to a particular image, right? I've shown you medical images, assigning labels like normal, abnormal, or grading the tumors, grade 1, grade 2, and so on up to grade 5, and like that. Also, I've shown you facial emotion or you can expression images, where your task is to assign a category, assign an emotion to a particular image. I've shown you a couple of food images, where your animal images, scene images, where your task is to assign a level, right? In case of animal classification, your task is just to assign a level, fine, or like tiger, giraffe, and all to a particular image. So what are the images that are involved in a traditional computer vision system? What will be given to you is a set of images. These are, let's say, set of images are given to you. These are all input images given to you. The very first stage you will find in traditional computer vision system is a pre-processing. And the next stage is all about feature engineering. Where you will find there are two stages. One is feature extraction, and one is feature dimensionality reduction or feature selection. And then followed by classification. This is a traditional machine learning based computer vision system. But what we are interested in modern computer vision is deep learning based computer vision system. I'll talk about different stages. I'll talk about the different stages and what are the weaknesses in this and why we are interested in studying this image enhancement today. Right. So given a set of images, your task is to first design a computer vision system, of course, to assign a label to particular image. So as you all know, I hope you have already got some idea of machine learning, where there are two stages, especially while designing the model or while building a model. One is training and one is testing. So we usually use the training images to build the model, and testing images we keep it for just evaluating or just to check the performance of the model. Right? Let's say set of training images are given to us, and as I mentioned, that the very first stage in any traditional computer vision system is nothing but pre-processing. What is the task of pre-processing here? Why do we need pre-processing? Right? So the goal of this stage, this pre-processing, is just to enhance the quality of the image. Right? Maybe the image is contaminated by noise. Maybe the image is nothing but dark in nature, or the contrast of these images, whatever is given to us in the data set, let's say, is poor. So to improve the contrast, because if you are not improving the quality of the image, you cannot extract the important patterns known as features from these images, right? So that is why pre-processing plays a very important role here in order to enhance the quality of the image, right? And that is why we need to study image enhancement techniques, where you will get to know about different kind of techniques used to enhance the quality of the image, so that the visual appearance of the image is going to be good, right? Whatever is given to us. There are a couple of tasks. I mean, you can enhance the contrast. If you can remove the noise, you can remove the blurring effect that is present in the image. Our main goal is to extract meaningful information from these images, right, through the feature extraction process. But if you are not pre-processing the image, so then you will be you will not be able to extract some sort of important patterns from these images, which are very, very important for us, right? So I've shown you a couple of such cases. The illumination problem, the dark images, where you will find a lot of difficulties in identifying important features. So pre-processing is a very important stage here. Similarly, in the next stage, the most vital stage in any traditional computer vision system is nothing but known as feature engineering. So where your goal is to extract the important, you can say, the crucial features or the patterns that are present in this image, right? So we don't want to use the raw pixels, whatever is present in the image, directly as the features, right? Features are always, in the traditional computer vision systems, are always represented in the form of a vector, right? So the simplest way to extract the feature is to just convert this two-dimensional matrix into a one-dimensional vector by just converting or by unrolling this two-dimensional matrix into a one-dimensional vector. So what you will be having a set of pixel values. But the image, if the image is having size 256 cross 256, having 256 number of rows and 256 number of columns, what will happen is the number of pixels you'll be having is 2 to the power 16. Right? And these raw pixels we cannot consider as a feature vector, because the number of features in the feature vector is going to be very, very high. You cannot directly apply the classification algorithms. That classification algorithm may take a long time to classify the images. At the same time, there are also other issues. Why we don't want to convert this image into a one-dimensional vector? In image, the spatial relationship is very, very important. The neighborhood relationship is very important. While converting this image into its one-dimensional vector, to make it as a feature vector, right? So you have lost some of the spatial information, which is very important. So then this process is not correct, right? We cannot directly consider these raw pixels as the features, right? We want the features. We want few features or few patterns of these images which can better represent this image. And the dimensionality of the feature vector should not be 2 to the power 16. It should be less than 2 to the power 16. So instead of taking the raw pixels, we are looking for some patterns, right, which can better represent the whole image. And that is what is known as features. There are different techniques we have for feature extraction. There's one session we have on feature descriptors probably tomorrow. So you will get to know more about the different types of features you can extract. The features could be of different type. The features could be a shape-based feature, geometry-based feature, texture-based features, color-based features, right? It could be of different types. Then what type of features you should extract from these images? It is purely application dependent. The kind of features, let's say you have extracted for a particular problem statement, may not work for other test statement. I mean, for other types of images also. So unless until you are a domain expertise in the field of feature engineering, you cannot directly decide that what kind of feature is going to be useful for extracting the patterns from the given set of input images. So there are different, as I mentioned, there are different algorithms we have. You might have heard about something called as ZLCM, gray level coherence matrix, LBP, local binary patterns, SIP, sort. There are different types of algorithms you will find in the literature for feature extraction. So how would you know? Statistical features are also very, very important. Textual features. So GLCM is a very, very, very popular approach to extract the textual features from the images, because texture plays a very important role here. Right? So let's say your task is to just classify, a cat versus tiger. So you cannot directly consider the shape-based features, right, to categorize the cat versus tiger. Although we know tiger is large in size, cat is small in size, but sometimes you may take, pictures closely, right, for the cat. So you may, in the image, maybe the cat is looking bigger. In the image, the tiger is looking, small. The cat is looking bigger. Size cannot be considered. I mean, the shape and the size cannot be considered alone as the unique features to categorize cat versus tiger, because the shape may be same for both. So what is different in this case is the texture of the tiger, or probably the texture of the cat. So textual features are very, very important, right? We'll also see the applications of one traditional machine learning based vision system, right? In that one hands-on session, right? How to extract the GLCM based features and how to process it through the classifier to design a traditional computer vision system. The major concern lies here: how would you choose the feature extraction technique, the best feature extraction technique? The second stage here is an optional stage over here in feature engineering, which is feature selection. Let's say by using some by concept, or let's say by using GLCM and other techniques, you have extracted 100 number of features, or let's say D number of features. That is feature 1 to feature D, which is D is less than 2 to the power 16, right? Less than, very, very less than 2 to the power 16. This could be 100, this could be 200, sometimes 1000 also, right? So it's a very small number compared to 2 to the power 16. Let's say you've extracted 100 features using different techniques or different feature extraction techniques. And then this particular stage, feature selection, says that there are some features which are irrelevant, which are unimportant, that are present in this feature vector. You can just remove those features. It's very, very important, because we do not know whether all features we have extracted are important or not. So these features, whatever we have extracted are static in nature. We have not looked at the output. We have not looked at the output, and we are not updating the features. We are only extracting the features. We do not have any idea whether this type of features is going to be helpful or not. You don't have option here change or to modify, to update the features. Only you can extract the features, and that is why it is known as static feature engineering. Right? You have just extracted the features, sometimes known as handcrafted features or hand engineered features, because you are manually extracting the features. And then again, you are trying to select a subset of the features. Out of D number of features, you want to select some of the features which are important for us. There are different types of techniques we have here. Either you can apply some subset selection approaches like filtering approaches, where your task is to identify a best subset out of D number of elements. You'll be having 2 to the power D minus 1 number of subsets. Right? You know that if there are D number of elements in a set, you'll be having 2 to the power D number of possible subsets. But I'm not considering the phi subset over here. So that is why there will be 2 to the power D minus 1 number of subsets you will be having. And out of 2 to the power d minus 1, you need to choose only one subset. That will lead us the best, or you can say the optimal set of features. Looks like a difficult task, but yes, there are algorithms available through which you can solve this problem. People have also used meta-heuristic algorithms. They've explored those. We have studied genetic algorithm, particles from optimization, differential evolution kind of thing. So they have used the binary version of those algorithms. Genetic algorithms by default is binary in nature, where the solutions are like in the form of 1, 0, 0, 1 like that, and we'll be having d. The dimension of the solution vector will be d, and where 1 means the feature is selected, 0 means the feature is not selected. And you need to identify the best solution, right, in the form of 1 and 0. And using this also, you can solve the problem. Feature selection problem. People have also applied here PCA, the principal component analysis, to reduce the dimension from D to D days. But here in this case, if you are applying PCA, the original features is not going to be retained, because this is PCA says it is nothing but the linear combinations of the features, right? So there are a couple of algorithms which can be applied in case of feature extraction, in case of feature selection, but we don't know which algorithm is going to be helpful here. There is a major concern here, how to choose the best appropriate, we can say appropriate feature extraction algorithm. This is a major concern here. Another major concern here is these features are static in nature. You cannot update these features, right? So you are not, learning these features. You are only learning the parameters of the classification algorithm here. After extracting the features, selecting the best features, you are passing these features in the form of the vector to the classifiers. This classifier again could be a neural network-based classifier, could be a support vector machine classifier, could be a decision-based classifier, could be a random forest-based classifier, could be Bayesian classifier, could be k nearest neighbor, could be anything. Again, there is a concern over here that which classification algorithm you would choose. Can you tell me? For a set of images, let's say for cat and tiger, which classifier I should choose to solve the problem? I know that there are algorithms which are very good. I mean, they perform well on different data sets like neural network. You might have seen support vector machine, random forest are commonly used algorithms to solve classification tasks. But no one can guarantee that yes, this is the algorithm which will always work, right? That means there is a concern over here. So there is a concern over here which pre-processing technique, feature extraction technique, which classification technique, and which combination of these algorithms are going to help me to best classify the samples, whatever is given to me. These are the concerns which you will find in traditional machine learning based system, right? But and another major concern, as I mentioned, that these features are static. You are not updating the features. You are only updating the parameters of the classification algorithms. Let's say you are choosing neural network, so you are only looking at changing the parameters W and B. W is the weights and B is the bias involved in different layers. You are not changing the values of, or you can say the values, you can say the features especially. So that is where we are interested in learning deep learning based computer vision system, where the features are not extracted, right? Where the features are dynamic, that means the features are updated by looking at the output, right? So along with the parameters of the classifiers, you can also update the features. You can also learn the features. You can learn the parameters of the classifiers. You can also learn the parameters of the, learn, or you can say learn the features instead of extraction or the static features. You'll be having dynamic features, and those features can be called as learned features, non-handcrafted features, right? And that is why everyone is interested in learning, or in solving the computer vision problem with the help of deep learning, where the features are learned, or where the features can be updated by looking at the response or by looking at the output, right? And in that case, the whole system is end to end learnable, because everything is learnable there, right? So you can learn the features, you can learn the parameters of the classifier, but this system is not end-to-end learnable. That's why these are not popularly used, right? But to appreciate the algorithms, right? I mean, the advanced algorithms, we need to understand the concept of traditional computer visions. Hope you have got some idea here, and we will also discuss these things in the hands-on session. Let us now directly jump to the pre-processing stage, and why do we need this image enhancement here, right? Pre-processing plays a vital role. So when I say image enhancement, of course, if we want to enhance the quality of the image. So if you look at this image, if I ask you what is, can you interpret this image? What is, if anything, any object is there in this particular image, probably you won't say anything because the image is dark in nature, right? Because the dynamic range of the image is very poor, right? So the contrast, you can say, it is in a dark image. So maybe the photo has been taken in a dark room. So how to enhance the quality of the image or this type of image? Because if I give you this type of image to you, you cannot extract, you cannot even predict that what kind of feature extraction algorithm I should consider to avoid this problem. There are of course few algorithms which are robust towards illumination, robust towards rotation, translation, scaling issues, but still it is difficult to find such an algorithm to identify important patterns in these scenarios, complex scenarios. Fine. So goal is very simple. I'll go a little bit fast. So goal is very simple here. In image enhancement, as I mentioned, we want, right, to enhance the quality of the image so that the results will become more suitable than the original image, right? But this processing technique, the traditional processing technique, what we will discuss today is application dependent. What do you mean by application dependent here? When I say application dependent, it means that the kind of algorithm which you have chosen for this picture, right, may not work well on other type of image, maybe on medical image, right? So we'll discuss later on. So in a broad sense, I can say the enhancement techniques, the image enhancement techniques can be broadly categorized into two different types. One is spatial domain-based techniques, frequency domain-based techniques. Spatial domain-based techniques, you will directly work on the pixels, right? And in the frequency domain, you need to first convert the image, right, into its corresponding frequency domain image by means of some transformations. You will see there is one session on it, how to use this, how to perform enhancement in frequency domain, where you might have heard about something called as Fourier transform or fast Fourier transform. You can apply Fourier transform to convert an image which is in the spatial domain to the frequency domain, apply some operations over here, and then apply the inverse Fourier transform to get back or to get the enhanced image, right? So applying some of the operations in the frequency domain image, or you can say the frequency domain output is very easy compared to the spatial domain. And there is an inverse also exists over here where you can perform some operations and get back to the original image. Fine. Yes. How can we mathematically define, right, the all enhancement techniques? The enhancement techniques, right, can be mathematically defined as g of xy is equal to t of f of xy. F of xy is nothing but the original image. That is the way how we can represent the image in the form of a two-dimensional function. T is the transformation function which is applied over this image to get g of xy. G of xy is the corresponding enhanced image, right, of f of xy. There are different types of operations. We can say processing techniques we have based on the application, based on the neighborhood we consider for this. Based on the neighborhood, or you can say based on the transformation function that is applied over a neighborhood of a particular pixel. So what are those types we have? The types are nothing but known as point operations. You can call it as a point processing techniques, local operations, and global operations. Very, very important. So these are the three operations, right? You can apply over a function or over an image to get an enhanced version of the image. What do you mean by point operation? What do you mean by local operation? And what do you mean by global operation? Let me just give you an overview. Let us first talk about point operations. So this is f of xy and this is g of xy. Okay, so point operation, every pixel in g of xy, what is g of xy? The enhanced version of this input image, right? So every pixel in g of xy is only dependent on the corresponding pixel in the input image. I hope you got my point. Let's say this is a transformation function which is only dependent on the point operation. That means every pixel in g of xy is only dependent or can be modified only by looking at the corresponding point in the f of xy. That is why the name is so-called point processing technique or point operations. But in case of local operations, very, very important, because convolution is also a local operation. And that is where actually you will get to know about convolutional neural network. This convolution is a local operation. So when I say it's a local operation, that means every pixel in G of xy is not only dependent on the corresponding pixel, but also dependent on its local neighborhood. I hope you got my point. Every pixels in the output image is not only dependent on the corresponding pixel in the input image, but also dependent on the neighborhood of the corresponding pixels. And that is why the name is so called here local operations or mask processing operations, right? This will be discussed later on. And global operations are like every pixel in the output image is dependent on all the pixels in the input image. Like the frequency domain operations, especially Fourier transform, right? Where every output pixel, right, is dependent on all the pixels in the input image. Those are known as global operations. Very, very important terms, local and global. CNNs, convolutional neural network, you'll get to know about it, are very good at extraction of the local informations from the image, because the convolution operation is itself is a local operation. But it cannot extract global informations because it is not a global operation, right? Because the convolution is always applied to the, a particular local region, which is the neighborhood of that particular pixel. Then, global is very, very important here, because sometimes you need both the local information and the global informations, right? I mean, basically the local features and global features. So how to extract those kind of things? You will also find its advancement, right, in the form of Bayesian transformers and all, which are very good at extraction of the global global features instead of the local features. We'll talk about it later on. I mean, how actually we can how we can extract both local and global information simultaneously. But now if you look at the complexity per pixel is a constant in this first case. In the second case, it is the complexity per pixels is p square if the neighborhood size is p cross p, right? And for the global operation, the complexity per pixel is n square. If the mn, because for every pixel you are considering all the pixels, then the image size is n cross n. So per pixel it is n square, and if you are having n square number of pixels, it will be n square into n square. That's the complexity, right? Okay, so we'll start with the point processing. I'll go a little bit faster here. I mean, I'll just give you the idea that what are point processing techniques, and these local operations especially will be discussed in another session, right? Neighborhood, I mean, just now we have seen that there are 3 types of neighborhood. There are 4 neighborhood, there are diagonal neighborhood, there are 8 neighborhood. So from now onwards, we are not going to use actually those type of terms. So probably we'll talk about something called as 3 cross 3 neighborhood, 5 cross 5 neighborhood, like that. So maybe this is actually right. You can this is the pixel which we are considering, and these are the 8 neighbors. And all together there are 9. So we can call it as a 3 cross 3 neighborhood of a particular pixels, right? So we'll talk about it later on. So we'll get to know about it in the session where the speaker will discuss about the linear filtering and all. Now let us start with the point processing techniques. So in case of point processing, I can say the neighborhood size is 1 cross 1. Can I say like this? The neighborhood size is 1 cross 1 because I'm only considering that corresponding pixel in the input image. I'm not going to look at other. I'm only going to look at the the central pixel, which we are considering, right? So I mean these operations are actually zero memory operations where you need not to store the neighborhood in some different array or different you can say memory. In this case, I can just modify the equation which I've shown earlier in the form in the form of g of xy is equal to t of f of xy. I have just represented, or you can say represented the same equation in other way, where s is equal to t of r. What is r? R is nothing but a particular gray value or particular intensity value of f of xy, and s is nothing but the corresponding output values in g of xy. I hope it is clear, right? R is nothing but the input pixel values, or you can say the s is nothing but the output pixel values, right? So there are multiple mathematical operations you can apply over the image to enhance the quality of the image. So you can see the operations like logarithmic negative transformations, logarithmic transformations, even the power law transformations kind of functions can be applied over the image to get the enhanced version of the image. But these are like, right, I can say a fixed kind of thing. I mean, where you can only enhance one particular type of image, right? I'll show you. I'll start with the identity function. You can see how the identity function looks and how the equation, right, can be how it can be expressed in the form of the equation. S is equal to T of S is equal to R. So this is R in the x-axis. S is the output pixel in the output image, right? So these are R is equal to S. So this is an identity function. So nothing will be changed if you apply this one, because identity function, right? But negative means what it is telling, that 0 will be 255 and 255 will be 0. You might have also seen, right, some negative images in some of the older camera, right? You might have seen this kind of photos, right? So negative image. Negative image is also very important in some cases, where you can see there are here, there are some images, right? You can say mammogram images to identify the breast cancers, right? So you can see these are actually the regions which are important for us, right? These are the important regions, I mean, to identify whether the breast cancer is present over there or not. I mean, basically these are the pathological regions. And there are some white and gray, there are less number of white pixels or gray pixels over here, which is dominated by the black pixels. And if I just take the negative of this image, so this, now you can see this, the appearance of this image is better. And now we can easily visualize these parts, right? So these parts are more clear compared to this part. It is just the negative of this image. That means 0 has been replaced by 255, 255 has been replaced by 0. But this picture is visually better than this picture, right? So it gives a better vision to analyze the image, right? So then when, when you will apply this image negative kind of operations, so you can apply when the black, regions are dominant in white, compared to the white and gray regions. Similarly, logarithmic transformations, it has expressions. S is equal to C is a constant, log of 1 plus R. You cannot take R value as 0 if you are not taking 1. So the log value will be undefined. And this is how the functions look like, right? So this logarithmic transformations is basically used for dynamic range compression, right? So sometimes you may find that the dynamic range of the image is very, very high. So if the dynamic range of the image is very high, so you cannot visualize, right, it using the display device. The display device won't support this kind of thing. And if you want to fully visualize this, so there may be some information loss. So this logarithmic transformation may be used to compress the dynamic range, so that most of the information will be preserved and will be displayed by your display device. Similarly, power law transformations can be expressed as S is equal to C into R to the power gamma. R is the input pixel value, S is the output pixel value, C is a constant, gamma is playing a very important role over here, right? So if the gamma value is 1, C value is 1, it is going to be an identity function. So how the function will look like, you can see over here. So this is how actually the identity function looks like. When C is equal to 1, gamma is equal to 1. When gamma value is less than 1, this is how the transformation functions look like. When it is greater than 1, this is how the transformation function looks like, right? So when the gamma value is less than 1, you can see a small range in the input pixel values is transformed, right, to a wider range over here. You can see over here, from here to here, right? A small range is mapped to a wider range, right? That means a small range which are darker is mapped to a higher range of pixel values in the output. If you consider this one, small range here is mapped to, that from 0 to, let's say here 50 is now mapped to 0 to 170 or like this in the output one. When the images are darker in nature, so you can just use the gamma value less than 1. Similarly, you can say when the images are brighter, you can use the gamma value greater than 1. Fine. So you can see over here, there's a dark image where most of the informations are not properly visible. So in this case, I'll use gamma value less than 1. So you can see the output just by applying a exponential function, or you can say a power law transformation, just by using this equation, right? I mean, just by applying r to the power gamma value, and you have to choose a gamma value, you can get this kind of output. You see the power of this, or you can see the potential of this, power law transformation. Similarly, if the image is washed out washed out means most of the pixels are brighter. So what you can do is you can take the gamma value greater than 1, and then you will, from this figure to this figure, you can see which one is visually better. So this one is visually better. You can easily find out these boundaries, these river lines and all, but which is not properly visible over here. So very, very important concept. Similarly, we are having a lot of other techniques, like contrast stretching is one of the most important technique which is useful in enhancing the contrast of the image, right? Which basically increases the dynamic range of the gray levels in an image. So let me show you the answers. Let me show you the output directly. Then you will get to know about contrast stretching and all. So this is a piecewise linear function, right? This is the transformation function in case of contrast stretching. Let's say this is from 0 to 255. This is the output one. This is S. This is R for you, and this is, let's say, or maybe this may be 50. This can be 30. This can be somewhere around 150. This can be somewhere around 210, like this. And these are the points that is given to us, right? And this is a piecewise linear function which we are using. If I take R1 is equal to S1, R2 equal to S2 over here, so R1, S1 is the coordinate over here. Like in our case, it is 50 and 10. And the R2, S2 is nothing but 150 and 210. So if they are equal, so it is going to be an identity function. Right? If I want, I can also change it. I can take R1 is equal to R2, S1 equal to 0, and then S2 equal to 255. So then I'll get this kind of transformation function, which is known as a thresholding function. So what do you mean by thresholding here? The values greater than this will be assigned 1, or let's say 255, or the value less than this will be assigned 0. And this is an input image, but I don't want this, right? So I don't want this. What I want to have a piecewise linear function. So for this, what should be the condition here? The condition should be R1 should be less than equal to R2, and S1 should be less than equal to S2. So this one is the condition to be satisfied to get this kind of function. Otherwise, you'll get identity function or thresholding kind of function, or close to those kind of functions, right? So this condition has to be satisfied over here. This will help us, right, in enhancing the contrast of the image. And why do basically we actually get a low contrast image? There are multiple reasons: because of the poor illumination, because of the low dynamic range of the imaging sensor which we are using. Sometimes even the aperture is not properly set. Maybe there's a small amount of light that passes through the aperture. That is why we're actually getting darker image or low contrast images. So this is a low contrast image. There are some grains that are present over here, and this is a low contrast image you can see over here. And from this image, we are getting this image with the help of a contrast stretching. You look at the difference between these two images. Even by using thresholding operation, just by converting this into its corresponding binary image, still there are some information, right, which are visible. This is visually better than this, but this is even better than this, right? So that means from this picture, we want this picture only by applying this piecewise linear function, right? So how to solve this? This point is 0, 0. This one is 0, 0. Let me choose another color. So this one is 0, 0, and this one is 50, 10. And right now how to find out, right? The formula: y minus y1 is equal to y2 minus y1 upon x2 minus x1 into x minus x1. What is x1, y1 here? That is 0, 0. x2, y2, that is 50 and 10. So you'll get a function, you'll get the y value in terms of x. And when the pixel values is between 0 to 50, you have to use this function. And when it is between 50 to 150, it is this. And when the pixel value is beyond 150 to 255, you have to use this. The coordinates of these values. So you have to scan all the pixel values and apply different functions based on the values, right? You are having. If it is less than 50, you have to use this equation. If it is 50 to 150, you have to use another equation. And if it is beyond 150 to 255, so you have to use another equation. That is how we can easily solve this kind of contrast stretching problem. Right? I hope it is clear to all of you. There are also gray level slicing techniques. If you want, you can only highlight a particular gray, right, a range of gray values, right, in between A to B. Let's say we are having values from 0 to 255. We only want to highlight, 50 to 100, and rest other either will be same, and rest others are either will be compressed or you can suppressed. Right? You can see over here where you want to highlight only one particular region. Here also you want to highlight a particular region, and other values are as it is. This is R, this is S, and here other values are suppressed to 0. There are two different ways to perform gray level slicing, where you want to highlight a specific range of gray levels in an image. Right? So there are a lot of applications you can see over here. This is the input image. There's a breeze, right, over the canal, and if you want to only highlight this breeze part, so you can just apply here, right, kind of transformations where you can only highlight this particular part and suppress the background. The simplest way to do this. Another applications, another way to do this. This is the input image of input angiography images, medical images. This is the output using the first transformation while suppressing the rest of the pixels to 0. And this is the second one while keeping the other pixels as it is. You can see over here. Fine. Okay. but in this case, actually, this is better. This is better because most of the informations are preserved in this case, especially the kidney and the blood vessels are preserved, but here it is not preserved. So what you can conclude in some applications, this is better, in some applications that was better. Fine. So these are all point processing techniques, right? Where for every, because whatever the transformation functions which I've shown to you, for every R there is a S here. Although you are following a function, but for every R you are getting an S value. That is why the name is so-called a point processing techniques. There's a difficulty also here that if I ask you to choose one particular technique, right? So it will be difficult for you to choose one particular technique, right? That leads to always better results. So, but sometimes we need to take care of the global appearance of an image. We want to enhance the contrast of the image, the overall image. So in that time, in that case, the histogram processing techniques are very much useful. The picture which I've shown, right, before, where all the pixels were looking, where all the pixels were looking black, but I have shown you this picture earlier, right, and you could not able to tell me that what kind of object is present in this image, but there's a baby in the cradle here. And why it is not possible to visualize these objects? Because the dynamic range of this image is very low. All the pixels are having values, let's say 0 to 15 or 0 to 20 or 0 to 30, and all values are close to 0. That means close to black color. And you cannot able to visualize all these things, right? So then what is histogram here, and how histogram is helping us or will help us in analyzing or in improving the global appearance of this image? We'll see in a couple of minutes. So I'll take only 5 minutes to finish this, right? So histogram is, this is in the right side, you will find the histogram. It is nothing but, you can see over here in the x-axis, you will find the intensity values or the gray levels or the color values, which lies from 0 to 255. In the y-axis, it is the number of times that pixel present, or you can see the occurrence of the pixel in that particular image. And you can see over here, most of the pixels are centered towards the left side. That means it is from 0 to 0 to 30 or 0 to 40 like this. And that is why we are not able to see anything in this image. This is an underexposed image. And this is an overexposed image where most of the pixels are right center. And the image I would show you later on. So then how can we define a histogram? I have already discussed. H of Rk is equal to Nk. This means histogram of a particular gray level Rk is nothing but Nk. Nk is nothing but the number of pixels, right? Number of times it is present. I mean, that particular Rk pixel is present in that particular image. That is what is histogram over here. And this is how, if there is a small image given to you where the pixel values lies from 0 to 9. I'm not considering the grayscale image where the pixel values lies from 0 to 255. I'm just considering a small image over here having size 4 cross 4. There are 16 pixels. The grayscale values lying from 0 to 9, and how to just draw the histogram corresponding to this image. You can see over here all pixel values are nothing but either 2 or 3 or 4 or 5. So this is how you can draw the histograms, how many times it is present in the image, right? And yeah, normalized histogram is very, very important here. Normalized histogram is nothing but we have seen P of R, H of Rk is nothing but Nk, but it is the probability of Rk is nothing but Nk upon N. So it will tell us the probability of occurrence of that gray. How many, what is the probability that that particular pixel is present in that particular image? It is nk is nothing but the number of times that particular pixel is present upon the total number of pixels we are having. This will give us the probability of occurrence, which is very, very important for us, right? So probability distributions are very important for us. Now I'll show you how the histogram looks like and what are the, what is histogram equalization technique, right? I'll quickly discuss what is histogram techniques and what is histogram equalization technique and why it is so popular, right, for enhancing the contrast of the image. Let's say there is a dark image which is given to us, and if you just find out the corresponding histogram, it is left centered. You can see over here the histograms are concentrated on the lower side of the grayscale, and if you are choosing a brighter image, so it is concentrated on the higher side of the grayscale image. Fine. In the x-axis, you will find actually the gray levels or the color values. In the y-axis, the number of times it is present, and sometimes even the y-axis can be represented in the form of probability of RK. So this is RK, right? It can be either NK, the number of times it is present, or P of RK. That is the probability of occurrence, right? So in that case, if you just add all those values, you'll get 1. That is the probability distribution you are talking about. It is very, very important, right, for us to design some of the algorithm. Fine. So now I'll show you another. So we've seen two cases. One is a darker case. One is a brighter case. I'll show you another case, low contrast image. What do you mean by low contrast image? We already discussed, right? What we discussed is when the dynamic range of the image is very small. And you can see for this image, the range is from here to here. The range is very low. Fine. And if you that is why actually we are getting a low contrast image over here, and this is a very good image which is known as a high contrast image or a good contrast image. So in the good contrast image, you see the dynamic range, right? It is not concentrated on either left side or right side or somewhere around the center or somewhere around one particular place, right? It is distributed across all RKs or all gray values. From here, we can at least conclude that the image having high dynamic range or having the distributions very similar to the uniform distributions, because you can see, if you see over here, the probability distributions is very close to, or not too far from the uniform distributions which you have talked about or which you have already studied in school level mathematics or college level mathematics. What do you mean by the probability distributions, especially uniform probability distributions? So what you need to do here is, if this type of histogram is given to us, if we can spread this histogram uniformly to us both the directions, if we can spread this histogram across all the gray levels, the contrast of this image is going to be improved. So how to do this, right? So there are two techniques which we follow to enhance the contrast or the overall appearance of the image. One is histogram equalization, one is histogram specification. So what is important for us is a histogram equalization, because this histogram specification is a trial and error process, right? It is what I can say, application dependent, and it's a trial and error process. It's not popularly used or widely used. What is used is histogram equalization. I'll show you. Well, let me show you first the outputs after histogram equalization. I cannot discuss all the mathematics behind it, but I'll just show you the steps to be followed to solve the problem within 5 minutes. So let me show you the pictures which I've already shown you. This is the darker image which I've shown you, and this is the input histogram. And what I already discussed, that yes, we need to uniformly distribute these values, especially, or this histogram across the gray levels, all gray levels. So see, this is the output image after using histogram equalization. A small histogram equalization technique can give us this kind of output from this kind of input. And now if you, after equalization, if you find out the histogram, it is been distributed across all the gray levels. Similarly, this is not a dark image, this is a brighter image. So brighter image, if you apply a histogram equalization over the brighter image, you will get this kind of output. You look at here, how better the image is compared to the input image if you're applying histogram equalization, but just by equalizing the histogram. The next one, there's a low contrast image where the dynamic range is poor, and if you just distribute it uniformly by using histogram equalization, so then you will get this from this output, from this input to this output. Another interesting thing I would like to highlight over here, that if you are applying equalization technique over high contrast image, where all information, the image is not a bad image, the image is a good contrast image, all the informations are clearly visible, and then the kind of output which you are getting after applying escalation is very similar. One thing we can conclude over here, that histogram equalization is such a technique which can be applied over all the images, whether it is poor images, whether it is good images, it can be applied, because after even applying this technique over a good contrast image, there is no information loss and there is no even impact on the output image. But there are some techniques, image enhanced techniques, please note it down, that can be applied. If you apply on the good images, it may lose some of the important informations. So you need to be very, very careful while choosing the image enhancement technique, right? So because you cannot decide, right, that on which image from a large set of images, from which over which image you will apply the image enhancement techniques. So you have to apply, right, because you have to make it automated. So that's why you have to apply the techniques over all the images. So these are the techniques which can be applied over all the images. Even on the good images, it is not going to give us bad results, right? So then how to just perform image enhancement using histogram equalization? Let me just show you the transformation function, because the transformation functions which already we discussed, we have seen it. So the transformation function in this case is just this one. What is L minus 1? L minus 1 is nothing but the L is nothing but 2 to the power k. You know that L minus 1 is nothing but the highest intensity values, and the CDF is nothing but the cumulative, right, probability distribution function, right? And these are the steps to be followed. Let's say this is an image which is given to us, and if you look at here, all pixels are sent, all pixels are between 2 to 5, right? All the pixels are either 2, 3 or 4 or 5. So how to distribute these pixels, right? This is a small image I considered just for simplicity, right, where every pixel values are either 2, 3, 4, 5. We'll see how histogram equalization will help us, right, in distributing those values. From, because there are only 4, so this can be at least distributed from here to here. So you can say after equalization, you can see 3. This has been distributed. The other values has been distributed to this 3, 6, 8, and 9. Right. So how is it possible? Just by using this transformation function, which is nothing but histogram equalization. How it is possible? So see, we are having 9 gray levels from 10 values 0 to 9. And then you can compute nk. What is nk? How many times 2 is present, 3 is present, 4 is present, 5 is present. Other values are not present. You can find out the probability of occurrence, right? It is there are only 16 pixels, right? 6 upon 16, 5 upon 16, 4 upon 16, 1 upon 16, and then you'll get the corresponding probability values. If you add them, you'll get, of course, the value 1. What is CDF? The cumulative value. Just multiply the cumulative value with the corresponding highest value, that is 9, and you'll get this kind of values. So these are the replacement. That means 2 will be replaced by 3, 3 will be replaced by 6, 4 will be replaced by 8, and 5 will be 9. So that is how we have distributed 2 to 3, 3 to 6, 4 to 8, and 5 to 9, like this, right? So this is how actually, if you take a grayscale image, apply the same steps, same number of steps to solve the problem, you can easily get to know about the changes, right, you have made to this image. Fine. So even in the literature, you will find there are two other variants of histogram equalization still in use by most of the researcher. One is AHE, and one is another variant, you can say CLAHE. These are the two techniques which people are, CLAHE is still popularly used by many researchers across the globe to enhance the contrast of the grayscale image, color image, whatever the image may be. AHE is adaptive histogram equalization, where you are not looking at the whole image, rather you'll be looking at some part of the image, or like, let's say some blocks of the image, and then you will apply histogram equalization in that block, and you have to repeat the procedure. CLAHE is something very interesting. If you want, you can just go through these research papers or go through these techniques. CLAHE is contrast limited adaptive histogram equalization. If people are still using this algorithm to enhance the quality of the image, right? So Okay, I will stop here. I think these are some of the references from where I've taken most of the contents, and mostly I've taken most of the contents from this book, Gonzalez and Wood's Digital Image Processing. This is the most popular and you can say the best book for digital image processing. So I'll stop here. If you are having any queries, I'll be happy to take it. I don't know. Let me check the chat box. Oh my God. I'm not able to operate this. Where is the stop sharing button? This is yeah. So just a second, just a second. I'll answer all your queries. Code sharing. Stop sharing. Yeah, fine. Let me check. Feature. Feature updation means weights and bias. No, 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 no. See, I mean, in CNN, of course, it is the question is from Pooja. The feature updation means weight updation and bias updation. No. So, in case of traditional computer vision, what I've discussed, it is not about weights and bias. But in case of deep learning, it is actually weights and bias, which are also involved in feature extraction stage, right? Because in case of convolution, the features are extracted, and those convolutional layers are also nothing but neural network layers. Can be considered as a neural network layers, where in the convolution, basically we have filters. Every filter is having some weights, and those, I mean, the filter values or the filter coefficients. Those filter coefficients will be known as weights, and every filter is associated with a bias. Yeah. Any other thing? How does feature updation is done? What is pooling? What is pooling? Fox, you cannot speak up unmuting. Yes, yes, yeah. We are really sorry for this that you cannot unmute yourself, because we have only 1 hour of time, right? Which we have given to all the speakers. So if one will ask, then others may not get a chance. At least we can read all the questions and we can answer all your queries. That is what is the major reason. And we have also a lot of what I can say participants. So that is what is the main reason, actually, just to save the time and all. We have not done this, right? So very nice explanation. Thank you so much. It was so clear, easy to understand. Okay, that's fine. Informative session. Please share PPT. Yes, of course, I will share. Which enhancement technique works for thermal images captured from high dynamic range thermal camera? And okay, so see, as I mentioned that yes, there are because these image enhancement techniques, whatever we have discussed, is application dependent that you need to think of if you are dealing with a high dynamic range based image, and if you want to really display it in a display device. So probably you may use those logarithmic transformation which I've discussed. But sometimes even you need to check that which of the algorithm we should apply over the SDR image, right? So because there are some algorithms which also usually takes a lot of time, so we cannot apply all those things, right? But not a problem. We can apply any techniques, and you will also surprised to know that even this image enhancement can be done using the advanced algorithms, right? So once you will learn these advanced algorithms, like especially convolutional neural network and Bayesian transformer kind of thing, so you can more easily think about how to also apply those kind of algorithms, advanced algorithms, to solve the enhancement technique. That is also possible, how to remove the noise and all. And also there are a couple of interesting applications which I could not able to discuss today. Which is a very important application, right? Like weather conditions, in different weather conditions, whenever you are capturing an image. So how to improve the quality of the image? Let's say there is there's a heavy rain in your town, and there's a surveillance camera which is installed, right, in your let's say institution, and something has happened, let's say. So how would you how would you identify the important things or some of the objects from those images or videos? Because it's raining heavily, you're not able to see anything, right? And similarly, you can also take other situations when there are hedgy environments, right? So especially in the winter season, whenever you are taking the photos, or whenever, let's say, you are capturing videos through the surveillance cameras and all, so it is very difficult to analyze the videos because of the hazy environment. Especially in the night, it is even more difficult. So how to enhance the quality of those images also plays a very important role. And there are also underwater images. There are several other images, right? Whenever you are taking images from the drone, so how to enhance the quality of the image? This enhancement itself is again a problem statement, right? If you want, you can also take up a problem related to enhancement and solve the problem. But enhancement can also play an important role while designing a computer vision system. So all these implementations I will discuss in the first hands-on session, where I will choose one particular a feature extraction technique, and where through which we will extract the features from the images, and then we will apply some of the classification algorithm to classify the images, right, into certain categories. So there I will discuss everything, the experimental setup to be followed, what is testing, training, validation, everything I'll discuss. And also I'll discuss about the different tools we have to implement all these algorithms, right? So what you can do, that those who have not started, so either they can, as I mentioned, that there are different environment through which you can implement all these things, whatever we have discussed today: how to load an image, how to load a data set, how to display an image, or how to there are functions available in OpenCV. Please try to either download OpenCV or install OpenCV, right, by using different tools we have. Otherwise, you can directly apply those functions if you are good at using Google Colab, right, kind of thing. So I'll discuss all these things actually later on in the first hands-on session. But yes, if yes, when we will get recordings for our, yeah, these are recorded. These are available in YouTube only. So we'll share the link with you so you can easily see, right? A lot of all these things are available freely on YouTube. So any other queries you are having? No problem. From MA Probin, I can see. Thanks a lot, sir. I missed a few moments. Can we have recorded? Yes, yes, yes. You have recorded videos. If you have not attended the lecture fully, because I think it was a long lecture, right? So this lecture will definitely help you to understand what exactly an image is, how it is being captured, what are the process involved to convert an image into right an analog image into its corresponding digital image. So and then there are a lot of things of work we have discussed. So what I have not discussed is the local operations. That will be discussed probably on third day by Professor Ratnakar Das from NIT Rourkela, and where he will discuss about what are filtering, basically what are mass processing operations, and global operations, especially how to apply Fourier transform over the image, and why actually I have kept this lecture, this Fourier transform. It is really important, right, to understand to analyze the image in the frequency domain. So you will also see the importance of the frequency domain while designing convolutional neural network. We have also done few works where we have combined frequency domain information in convolutional neural network, right? So that means we have analyzed the features in convolutional neural network in both spatial domain and frequency domain. And there are also a lot of, as I mentioned, benefits of analyzing the features at frequency domain, right? So, I mean, you can just design even the convolutional neural network, whatever the new deep learning algorithms we have in both spatial domain as well as frequency domain. That's what we did, and we have been working on this particular problem. So you need to also understand the concept of this frequency domain as well. So I'll stop here. I hope there are no other questions, and thank you very much for joining the today's session. So I request all of you to please take out time and attend all the sessions. So probably from tomorrow you will even find the better lectures by professors from IITs and all, right? And I will also take few hands-on sessions and few sessions on convolutional neural network, especially convolutional neural network for image segmentation and all. So I would request all of you to please attend all the lectures possible. And because although I know that yes, you will get the videos, but interactions, like you are interacting with me, you are asking me questions, so that will help you a lot in future, right? So thank you all. So good night. We'll meet tomorrow at 4 p.m. Thank you.